Okay, very quick video. I did a few exercises um, of structure and interpretation of computer programs. I did exercises 1.3 and 1.5. So let's see them very quickly. So the first one, exercise 1.3, says define a procedure that takes three numbers as arguments and returns the sum of the squares of the two larger numbers. So this is not very difficult, is quite easy. I think this exercise is useful uh, just to get used to the prefix notation, to the syntax of scheme, and but it's not. It's an easy exercise, and also it's helpful to get used to um, the conditional procedure, conditional procedure. So the first thing that we can do is to define the square procedure, which is this one. So basically, the square procedure takes one argument and multiply it by itself. Then we can build up on this procedure and define the sum of square procedure, which takes two arguments, a and b, and returns the sum of two procedures, square A and square B. So here we start to see what has been introduced in the book right from the beginning. So the fact that we start with simple ideas and we compound, we build up from simple ideas to get complex ideas. So in this case, this is of course only an example. We start with a very simple procedure, and then we define a procedure that builds up on this simple procedure to have a more complex one. So we have sum of squares, and we can check that our procedures do what they are intended to do. So for example, we can check that square 2 gives 4 and square 3 gives 9. And then we can also check that sum of squares 2, 3 gives 4 plus 9, 13. Then we have to define the sum of squares of the two largest numbers. So remember that the text of the exercise reads: define a procedure that takes three numbers, so three arguments, and returns the sum of the squares of the two larger numbers. So here we have to define the procedure sum square to largest. We are using three arguments, A, B, and C, and we use the conditional procedure. The conditional procedure and also the logical operator AND. So here basically is we are saying that if B is greater than A, so if B is greater or equal than A, and C is greater or equal than A, then return sum of squares of B and C. Of course, because B and C are the largest numbers in the among the triplet A, B, and C. A, B, and C. If this condition is not doesn't evaluate to true, we are going to, the interpreter is going to evaluate the second condition, which is if in this case A is greater or equal than B and B is greater or and C is greater or equal than B, then A and C are the largest numbers in the group, so return the result of the procedure sum of squares of A and C. Otherwise, so even if this condition, this procedure, this condition does not evaluate to true, return the default condition using else, so sum of squares of A and B, because if these two conditions didn't evaluate to true, it means that the largest numbers are A and B. And this is it. We can check. I did a few examples. So if we try to run this exercise, Racket is a modern dialect of Lisp, and using this I don't know how to define this. With this command, we can tell Racket to interpret the code in a way that is compatible with Scheme, because Racket is a descendant of Scheme. So Racket, and we run the file, and we see that square of 2 is 4, square of 3 is 9, sum of square of 2 and 3 is 13, and square of the two largest, if the provided numbers are 3 to 1, is 13, which is correct because the two largest are 3 and 2. If the provided numbers are 10, 9, and 11, the result is 221, because here the largest numbers are 10 and 11, so 100 plus 121. And in the end, finally, if the provided numbers are 4, 5, 1, the result is 41, because it is 16 plus 25 equal to 41. And this is it for the exercise 1.3. And exercise 1.5 instead is more conceptual. It is very helpful to understand the difference between applicative order evaluation and normal order evaluation. So let's read the text of the exercise 1.5. Ben Bit Diddle has invented a test to determine whether the interpreter he is faced with is using applicative order evaluation or normal order evaluation. He defines the following two procedures. The first one is the definition of P, which is which is itself the call of P. Okay, sort of here we can see recursion. Okay, And then the definition of the procedure test that takes two arguments, x and y, and if x is equal to 0, um, um, returns 0, otherwise it returns y. And then he evaluates the expression test 0 and p. What behavior will Ben observe with an interpreter that uses applicative order evaluation? What behavior will he observe with an interpreter that uses normal order evaluation? Explain your answer. So let's start by looking at the first definition. This define P, basically calling P, calls P again forever. So basically P is never returning a value. In the case of applicative order evaluation, what the interpreter does is evaluating the arguments before applying the procedure. So basically, when you run this test 0p, the program never terminates. You have infinite recursion. Instead, with normal order evaluation, what the interpreter does is not evaluating arguments before applying the procedure. So basically, when you run test 0p, the interpreter expands it to if 0 equals 0, then 0, else p. And basically now the interpreter evaluates the condition 0 equals 0, which is true, and thus can return 0. And the alternative branch, which is the infinite recursion p, is never evaluated. So this is very helpful, and indeed, if you, now this file is a total mess, but if you try to run in the interpreter these lines, define P, define test, and then test, you can see that the program never terminates. So this means that my interpreter, Racket, is using an applicative order evaluation. It is evaluating the arguments before applying the procedure, and then when it's evaluating the P, it gets stuck in an endless recursion and never terminates. And this is it, a very quick video to show you these two exercises. So goodbye and ciao ciao.